Hello there and welcome to the second episode of my RTS game series. In this video, we'll be implementing grid building system. Due to the complexity of the system, I have divided it into three parts. In the first part, which is this video, we'll be implementing a building system and a grid system. In the second part, we'll add support for multiple buildings and grid hotkeys like Age of Empires 2. In the third part, we'll add support for blending terrain. Since it requires terrain, we'll add it after world generation. Before we begin with this episode, I want to highlight a few changes I've made since the last video. Input mapping is now called controller mapping. The movement keys have been changed from WASD to the arrow keys. The rotate action key has been changed from right mouse button to left alt. Disclaimer: this video contains a fair bit of math, but instead of shying away from it, I recommend you to understand it. With that out of the way, let's begin this episode. First of all, we'll create the selectable class, which will be the base class for all buildings, units, animals, and other objects. It will be deriving from the actor class. In selectable.h file, we'll create selection state enum with none, hovered, and selected states. In the selectable class, we'll add scene root and selection mesh. In the constructor, we'll create scene root and set it as the root component. Next, we'll create selection mesh, set it as the child of root component, and set it slightly above the ground. We'll also initialize it so that plain mesh is its default mesh. We'll also disable collision. Next, let's add two materials, one for hovered state and another for selected state. Also, add a private selection state variable. While we're at it, let's declare two functions for getting and setting selection state. In getSelectionState, we simply return the selection state. In setSelectionState, we'll update the selection state and use a switch statement to go over all possible cases. If the selection state is none, then we do not care about the current material applied to selection mesh. We simply hide it. If the selection state is hovered or selected, then we assign the appropriate materials before showing the selection mesh. In begin play, we'll set the selection state to none. Now that we have created these events, we need player camera to call these events. In player camera, create a function called getReposition. As the name suggests, it outputs the reposition, or more accurately, the reimpact point. Along with that, we would also like it to return the actor that it hit. Inside the function, we get the mouse position and the projected to world. Then, using line trace, get the impact actor and the actor hit. Create an input action that is called when left mouse button is pressed, along with two private functions, mouse select and mouse hover. Find mouse select to left click action. Inside this function, we'll call getReposition and obtain the reposition as well as the actor hit. After casting this actor to selectable, we'll select that entity. We do almost the same thing in mouse hover. Instead of calling select entity, we call hover entity here. Make sure to call mouse hover in tick. It would also be nice to have a few materials for different selection states and different selectable types. For example, a building with square borders or a unit with circular borders. Fortunately, these aren't terribly complicated to make. We'll be using custom node in Unreal's material graph, so the code will be in HLSL, which is fairly close to C++ in syntax. The next challenge on our way is how do we describe square borders in terms of UVs? The answer is actually really simple. The region where the x-coordinate is less than border width and the region where the x-coordinate is more than 1 minus border width represent the border in x-axis. Extending this to 2-dimension gives us the desired result. The HLSL code for that is simple as well. In the material graph, make sure to add 2 inputs in Properties panel. Creating hovered borders can also be achieved by using fmod. The code for that is on screen. In the material graph, make sure to add inputs in the Properties panel. Similarly, we can use the distance from the center to create circular border. The border would be in the region where the distance is less than half but greater than half minus border width. In the material graph, make sure to add inputs in the Properties panel. Again, using fmod, we can create hovered border. In this section, we'll be making the core of this system. Our goal is to be able to create preview buildings, dynamically change the position of the preview, and place the building. For now, we'll support placing just one building. Firstly, we'll create a data asset class called building data and an actor class called building. The data that we'll store here includes name, ID, dimensions, and the blueprint subclass of the building class. In its source file, we only need to include the headers. Next, we'll create another data asset class called building collection. We'll add a building data array along with 2 functions, sort by ID and get building data. We use the following syntax to sort the building data in ascending order based on their IDs. In get building data, we simply return the building data at the index of their ID. In building.h, create an enum called placement state with placement allowed, placement blocked, and placed states. In the building class, we'll create building mesh. building data, and see materials. In the constructor, instantiate building mesh and set it as the root component. In begin play, if the building data is not null, we'll scale the selection mesh of the parent class to match the building dimensions. Now we'll add placement state variable and a function to set the set variable. Inside this function, we'll first update the placement state and then use switch. In all cases, we assign the appropriate materials to the building mesh. Next, we'll make an actor class called building manager. Create building collection, preview building, and preview building data variables. Now we'll make 4 functions, one for creating preview, one for updating its location, one for confirming it, and the last one for destroying it. In create preview building, we'll get and assign the preview building data, then spawn a building blueprint actor. In update preview location, we simply set the preview location after a safety check. In confirm preview building, we'll first add a safety check, then set the placement state of the variable to placed, and finally clear the references. In destroy preview building, we'll destroy the preview and clear the references. In player camera, create an input mapping context called building mapping and an input action for Q key. We'll also create a private boolean to see if we are in building mode. Here we'll define the same functions as we did in building manager, except confirm preview building, which we'll call directly. Let's also add a callback function for Q. Before we move forward, we'll create a function that searches the world for building manager and returns it. In setup input component, make sure to add the mapping context as well as bind the Q input action to its callback function. In create preview building, after adding a safety check, we get reposition and call a function of similar name in building manager. The same thing happens in update preview building location. In destroy preview building, we simply call the building manager to destroy the preview building. In function Q, toggle building mode and depending on its value call either create preview building or destroy preview building. In begin play, get the building manager from world and set it to the variable. In tick, we update the preview location. Let's compile and run the game. Oh no. Why is the building moving towards the camera? After banging my head for an entire day, I finally found why this happens. So it turns out that in update location, the ray hits the building and thinks that it is the ground. So it moves the building to the impact point, moving the building upwards and towards the camera. This repeatedly happens, causing the bug. Fortunately, fixing this is pretty simple. We just add a new collision channel in project settings. We use a macro in building.h to refer to this custom channel. In the building constructor, we'll set the collision channel to the buildings channel. In mouse select, we'll add building collision channel to the object parameters. Now the bug has been solved. One final thing we need to add is the event to confirm the preview. In mouse select, we'll confirm the preview building and set the building mode accordingly. Let's test it in editor. It works perfectly. Next up, let's snap the buildings to a grid. Our goal is to calculate the midpoint of the building such that visually the building always remains snapped to the grid. Assuming the simplest case in 1D, where the cell size is 1, we'll divide the problem into two cases, each for buildings with even and odd dimension. In the case of buildings with even dimension, we can observe that the midpoint of the building is always an integer. Thus, we can simply round the ray position to obtain the position of the building. It is pretty easy to extend this to a grid where cell size is not 1. We simply divide the ray position by cell size inside the round function and multiply by cell size outside the round function. The code for that is self-explanatory. In the case of buildings with odd dimension, we can see that the midpoint of the building is exactly halfway between two integers. Taking the average of the seal and flow values of the ray position gives us the position of the building. Again, it is very simple to extend this to a grid where cell size is not 1. We simply divide by cell size inside the seal and flow functions and multiply by cell size outside. The code implementation looks something like this. In create preview building and update preview building location functions, we'll define a new vector called location. We'll check if the x and y components of the array position are even or odd, and use the newly created functions to set the location. For now, we'll set the z component of location the same as array position. In begin play, we'll set the cell size to 100. Upon compiling and running the game, we'll see that the buildings are now snapped to the grid. In this section, we'll create a grid system so that we can keep track of the buildings we have created and prevent buildings from overlapping. Let's create a grid class deriving from object. Define 4 private variables: length, breadth, cell size, and grid array. Note that we are using a one-dimensional array and not a two-dimensional array. The reason is that 1D arrays run faster than 2D ones. Declare initialize function in which we'll set the respective properties. If the cell size is 0 for some reason, then we'll correct it to 1. Finally, we'll set the number of elements in the grid array to length times breadth. We'll now make getter functions for length, breadth, and cell size. Sharp-eyed viewers will notice that the corner of the grid array is at origin, but we need to keep the grid centered at origin. Hence, we need to convert between grid position and world position. So, we'll declare two functions for precisely that. Before we begin defining these functions, we need to go back to the drawing board and find a math equation that describes the relation between grid space and world space. Please note that we'll be ignoring the z component of world space. First, let's convert world space to grid space. The very first thing that may come to your mind is to divide the world space by cell size. Great. But we still need to address the issue that our grid is not centered. To center, we simply add length or breadth halved. To obtain world space coordinates, we can easily rearrange the equation to make world space the subject. The code for both the functions is self-explanatory. With the help of these functions, we can add a few helper functions, starting with getIndex. We'll create two versions for grid and world spaces. Thankfully, these functions don't require a lot of math. For getting the building at a particular position, we'll use getBuilding function with some safety checks to make sure that the position we received is actually in the grid. The code for setting the building is similar. In Building Manager, we'll reference an actor which we'll be using to visualize the bounds of the grid. We'll also make a grid variable and a float to cache the cell size. Next, make a function called initializeGrid. Inside of it, we'll create a new grid object, initialize it, and cache the correct cell size. Also set the scale of bounds actor to match the grid size. Make sure to call this function in begin play. Now we'll create a new function called isPreviewLotEmpty. Set its return type to bool. In this function, we'll check if the grid position that the preview building occupies is empty. To do this, we'll find the starting location in grid space. Then we'll loop over all the cells occupied by the preview building and check if it is occupied. If it is, then we return false, otherwise return true. In confirm building, we'll check if the preview lot is empty or preview building is null. If it is, then return false. Otherwise, we similarly loop through the cells and set their value as the preview building. In create preview building and update preview building location, we'll check if the preview lot is empty and set its placement state accordingly. Compile the code and test this yourself. Another small feature we want to add to our system is the ability to rotate buildings about the vertical axis or yaw. In Building Manager, we'll add a boolean variable that indicates if the building is rotated in such a way that we need to flip the building data's dimensions we are using. Such a rotation could be 90 degrees or to 70 degrees. We'll add a function to update preview rotation that takes two parameters, the current rotation and the target yaw. Inside, we'll add a safety check for preview building. Then we'll set B change dimensions and the axle rotation. Next, we'll create two functions, getBuildingDimensionX and getBuildingDimensionY. Inside these, we return the correct dimensions if B change dimensions is false, and return the flipped dimensions if it is true. Finally, we'll replace the expression where we get the building dimensions from the building data with the above created functions in create preview building as well as update preview building location. In player camera, we'll add two quaternion variables, one for target building rotation and another for current building rotation. Now, add two input actions for rotating the building left and right. Also create two functions for the same. Inside these functions, we'll add or subtract 90 degrees to the target rotation based on the direction of rotation. Make sure to set up these two functions as the callback functions of their respective input actions. Next, we'll create a function called update preview building rotation that takes delta time as parameter. Inside, add a safety check for building manager. Then we'll use quaternion slurp to calculate current building rotation. Lastly, we'll add a callback to the building manager to update the rotation. In the editor, we'll create two new input actions for rotating the building either side. Assign the actions any key you like. I personally went with numpad arrows, that is 4 and 6. Make sure to reference these in the player camera blueprint. Now run the game. If you found this video helpful, please like, share, and subscribe. I'll see you in the next episode.